Hey everybody, today we're looking for a positive integer that will make this quotient also an integer, and this is a 6th degree numerator here. So we want a positive integer x greater than 0 such that this evaluates to an integer. Now just notice, get your feet wet, x equals 0 leads to 23 over 5, right? So that's the simplest try, but that is certainly not a member of the integers, right? In fact, it's a rational number, right? Okay, so we need some sort of methodology to do this. In the I don't know of a way to do this that's not just ad hoc unless we do long division, okay? And again, I didn't go through the steps of the long division, but when you do the long division, you get this piece right here, which would be what the quotient, or I guess the dividend, or whatever it's called. But anyway, this piece right here is certainly a member of Z for all integers x, right? We just need this object here to be a member of Z, all right? So that's really the whole problem. And so that's what I wrote right here. This can be a member of Z if and only if this this remainder over divisor expression is also an integer. Okay, so this is certainly the truth. And so we set him equal to an integer k. We get this equivalent statement here, and we multiply it out. We get a quadratic with this parameter k. Okay, we get a quadratic with the parameter k, and we can write down the discriminant. This is the discriminant right here. Now, we have two conditions we're going to impose on the discriminant. It has to be greater than or equal to 0. That's to avoid negative numbers, right? Avoid complex. This avoids complex. We're not interested in complex x. We're interested in just integer, positive integer x. So this avoids complex x values, okay? And then also we need it to be a perfect square. Otherwise, you would have the same problem with irrationals. This would avoid irrational solutions. I'd be in heaven if I could figure out a faster way to write. I need a different program. I'm just using the mouse here in Word. So this is irrational. All right, so those two conditions must hold in order for x to be an integer. Okay, so let's keep going. Now, so what do we do right here? Okay, what we're just doing is trying to get an upper bound on our k's right here. And so in that, towards that, we'll end up with, if you look at the arithmetic that happens right here, you would end up with 19k squared. Okay, 19k squared, what, plus 14k, I think. Has to be less than or equal to 33 squared. Okay. I think that number's 1,089, but it's not so important really. All right, so again, this gives us kind of an upper bound circumstance. And if you go through the possibilities here, there's the only k's that are possible would be k equals 0. And again, I won't go through all this work. It's just kind of grinded out arithmetic. 2, 3, 4, 5, 6, 7. Like that, okay? You know, it turns out the only one that works is actually k equals 4. Now, I'll come up here and show you why. If you take k equals 4 right here, again, if we look at k equals 4 in this piece where we're trying to make it equal a perfect square, okay, this would be 29 squared right here. And let's see, minus 4 times 4 is 16, and then you have 16 times 17 is 112, I believe. 112, right, folks? If you put a 4 right here, that's 16. You put a 4 here, that's 20. 16 times 7 yeah, 16 times 7 is 112. Now this ends up being 729. So whoops, this is k equals 4. Sorry, folks. So k equals 4. K equals 4 gives you this, but this ends up being 841. I think 841. Or no. Is it 729? I think. Let me erase that again. Okay, so this is 729. And yeah, I wrote the rhythmic down. I'm just looking where I wrote this down on my paper here. Yes, this is equal to 841 right here. Minus 112. Okay, and then that 729, yes. Okay, and what is that? That's equal to 27 squared. See? So our m would be 27, right? Not that we, okay, but what's more important here is we know that k equals 4 is these are the only possible non-negative values that'll work based on this bounding statement right here. K equals 4 is the only one that does work, okay? And so if you put k equals 4 right here, we get 4k squared, or 4x squared, minus 29x. Okay, y'all, I'm getting 420, that's 7 right here. Okay, and so we're rooting for this to, if our logic's not flawed, this should be something that factors. So if it's going to admit a factorization, it has to at least take on this form here. And you can just see that it's going to work out with the 28 here and the 4. So what do we need? Minus 1 here, right? You'll see how when you multiply this out, it all works out, right? Oops, I can't. Okay. Okay, and so what does this result in? This results in x equals 1/4. But notice that's not an integer, okay? It's not an integer, not a positive integer. Okay, but we do get x equals 7, which is a solution. And I didn't even check it. It's guaranteed to work. None of the math we've done is wrong here that I can tell. So x equals 7 is our answer. Now, y'all, there are one of the very excellent viewers of the channel noticed that there's some negative solutions also. I just went for the positive, but if you want to, you can. I think there's a couple of negative solutions also. Okay, I think there's some negative values of k that satisfy this condition. Okay, so anyway, if you guys feel like checking, you can. I'm not going to worry about it. X equals 7. If you substitute x equals 7 into this expression, you will get an integer. I don't know the value of that integer, but the math is unassailable, I think. And so x equals 7 would be the only positive solution, I think. Okay, probably the only, so it's unique as far as positive solutions goes, but there are some negative solutions if you want to check on those. Okay, thank you for viewing.